Okay, thank you. Okay, great. So thanks for the invitation to speak. So this is joint work with, I hope you can see that better on your screen than I can on mine. Very light grey font saying Evis Kramer is the first author, so he's at the University of Reading, and Tom Thorne at the University of Surrey. And this work is funded by NERC. So many thanks to them. It's part of the Landscape Decisions Programme, where we're looking at making better ABC algorithms for calibrating models. I should say as well, there's no references in this talk, so all the references are in a draft paper that I've put in the chat. So if you want more detail, then do have a look at that. It's by no means complete, but it has got all the references. Okay. So the overview of today is to look at an introduction to ABC, in particular, why it's a pseudo-marginal algorithm and what the implications of that are. To look at a previous paper, which is called a rare event approach to high dimensional approximate Bayesian computation, that has one of the key ideas of this talk. It is based on that. And then the other thing is the new approach, the SMC squared approach, that I'll spend the second half of the talk on. So to fix notation and aims, we're trying to estimate a parameter theta. It's got a prior p. We've got observed data y. So we're looking at the posterior distribution of theta given y, which we'll denote by pi. We're going to use x's in the talk. X is on the same space as and these are usually going to be simulations from a model for the data that we're going to denote by f sub theta. So it's essentially the conditional distribution of y given theta. Okay. So in standard Bayesian inference, of course, we can usually evaluate the model pointwise at theta, and we call it the likelihood, and then we do our MCMC or whatever else we're going to do. ABC is set up to address the problem of what happens when the model can't be evaluated pointwise at theta, but where we can simulate from the model for a given theta. And the intuitive idea of ABC is to, rather than the standard evaluating the likelihood in the standard way, to simulate from the model for whatever theta we're interested in, and look at the statistics of the simulation. So look at the statistics of the simulation X, compare them to some statistics of the real data Y. And if the statistics of X look kind of like Y, then we say that this theta is plausible and we treat it as like it's a sample from the posterior. Okay. So what we'll see is that when we're doing this, we're in fact using an approximation to the likelihood, and in fact we're estimating that approximation, and we're going to call the approximation the ABC likelihood, and we'll call the estimation of that the estimated ABC likelihood, and this will give us the ABC posterior. Okay, so here's a standard algorithm for doing ABC in practice. This is the ABC-MCMC algorithm. To fix notation a bit further, we've got pi epsilon here. Pi epsilon we call the ABC kernel, and that's a way of writing down that we want to give more weight to things that are closer to the real data. So we're going to use this kernel to weight our simulations X, and essentially this is going to give us this is going to be bigger when X is closer to Y, and it's going to have its maximum value usually when X equals Y, and it's going to be symmetric about that, and it has a bandwidth epsilon, okay, or sometimes called a tolerance. So the easiest way to think about this is as a uniform distribution. So what's going to happen is that when y and x are close, then we get a non-zero value for that uniform distribution. And when y and x are far away, this is going to be 0. Is there a big problem with fan noise in the sound, by the way? Shout up if there is. I'll move where my laptop is.
Seems fine.
It's okay, good. Okay, it's very noisy at this end. I'm glad it's not so bad on the video. Okay, so we've got this uniform thing. So if y and x are close, then we get a non-zero value. If they're far away, we get a 0 value. And ABC-SMC works like this. So it's an MCMC algorithm for exploring theta space. So you simulate a theta, and then for that theta, you simulate. Let's see if this works. No, highlighted. Okay, there we go. That works. You simulate from f. You simulate an x from this f, and then you have an acceptance probability that looks like the usual Metropolis Hastings acceptance probability, but where you have this term at the end here, which is the ratio of the ABC kernels for the previous iteration and the current iteration. So instead of this is, of course, where the likelihood would usually be. So instead of the likelihood, we're looking at the whether the x star is close to the y in the numerator here. And if that's non-zero, then there's a chance that we'll accept this. If it's 0, then of course we'll reject this move. Okay. So that's what people implement. It's been well known for quite a long time now that what you're doing when you do this, you can think of it as being an estimation at every iteration, every time you move theta, of this likelihood here that we'll call the ABC likelihood. So this is an ABC likelihood with bandwidth epsilon. So I've missed out the epsilon at various points in the notation to hopefully so we don't have too many subscripts flying around. So this thing here is sort of the thing that we're estimating. And when we're doing ABC, what we're doing when we do this simulation from the model and then evaluating the kernel is we're looking at a Monte Carlo estimate or an importance sampling estimate of this integral. Okay, so we're looking at an importance sampling estimate of this integral. How does that work? Well, we have a proposal of f, and we have a target of pi epsilon times f. Okay, and so what we're doing when we do ABC is for every theta we look at, we're using an importance sampler with a single point to try and estimate what this likelihood is. So we're simulating from f, and then we're evaluating pi epsilon. So we've got a noisy estimate of this ABC likelihood, and that's the sense in which it's an estimated ABC likelihood. Okay, so what are the challenges in ABC? Well, some of these are sort of solved challenges, but these are very, very broadly speaking where the research falls in this area. Some of it is to do with exploring the space of theta, and over the last 15 years or more even, most of the methods that we use for exploring theta space in the standard setting have moved their way over to the ABC setting. So we've got rejection sampling, importance sampling, MCMC, sequential Monte Carlo, population Monte Carlo, and others. But there's also work on what the effect of using this approximate likelihood is. So for starters, this likelihood here, the one that was on the previous slide, is not the true likelihood, right? We've got if this kernel here, if this ABC kernel, this pi epsilon, was a delta Dirac, so it was purely had weight where y equals x, then this integral would give you the exact likelihood that's defined by f. But we don't have that. Instead, it's more spread out than that. We have a bandwidth that's bigger than 0. So we don't just get a point mass, and this isn't going to be the true likelihood. It's going to give us something. I mean, if we think of epsilon being really big here, and all of these things getting equal weight, then we'd have the prior. This thing would just have no influence whatsoever. So essentially, we have something between the prior and the posterior when we use this. So that introduces a bias. We also have some variance due to the fact that we're estimating the likelihood with this sample rather than using the exact ABC likelihood. So that's the kind of thing that has implications for how well our algorithms will mix. Oops, cancel. There we go. Okay. Okay, so so a way of seeing this, or aspects of this, is that ABC is a pseudo-marginal algorithm. So ABC is using an unbiased estimate of the ABC likelihood in place of the true ABC likelihood, and because of all the work on this, we know that, well, not all the work, I mean the initial work on this by Gareth and Christoph, we know there's no additional bias due to doing this. And we know that when we have a larger variance for the estimate, it will tend to make the ABC or the MC-MC algorithm in which this is embedded less efficient in general. So in ABC, what we have, in fact, what we end up with is a bias variance trade-off. And this is in epsilon. So if we choose epsilon to be very big, then a very biased answer, because it's only when epsilon's small that we go towards the true posterior. So if we make epsilon bigger, then we get more bias. So we'd like to make it smaller, but if we make it smaller, then it turns out that the variance, estimated ABC likelihood, will get bigger. Okay. So that gives us a problem. It means our ABC-MCMT is going to be less efficient, usually. So this gives us a bias variance trade-off for ABC. And another factor that's important is the dimension of the data here. So if you have a big data set here, then if you look at the ABC kernel, that's comparing two things in a high dimensional space. And so we end up getting a poorer importance sampling estimator. We're doing importance sampling in a high dimensional space. And in fact, that we're going to need an exponential number of importance points to stabilize that variance. There is a way of getting around this to reduce the dimension to avoid this variance blowing up, and that's to use summary statistics. But of course, if we do that, if those statistics aren't efficient, if we reduce the data to those things before comparing it, then that introduces another bias. Okay, so what can we do about that? Well, because ABC is a pseudo-marginal approach, there's an obvious thing we can do, which is to just simulate more times for every theta. So rather than just simulating once, let's simulate more times and average the ABC kernel. And that's still going to be an important sampling estimator of the likelihood, of the ABC likelihood. It's just going to have lower variance. So if we've got parallel computing available, then that might be useful. But then there are questions there as to, are we better looking at more thetas and one simulation for each, or are we better looking at many simulations for each theta? So it can help, but maybe not a lot, especially when the dimension of the data gets big. Just doing more importance points is, we need an exponential number in the dimension to stabilize the variance. So what we're going to try and do in this talk, well, the first bit of work, the rare event stuff that I mentioned before, is a way of getting around this issue to some degree at least. So let's talk about that first. So that's our aim, right? We're trying to be able to do ABC with higher dimensions somehow. So the thing that we're going to use, this is a construction that I think I first saw in a discussion by Christophe Andrieux and Anthony Lee and Arnaud Doucet of Dennis Prangle's red paper with Paul Fernhead in Series B. So they mentioned this possibility, and it's been used in a few ABC papers since. It's to look at the simulator as a deterministic transformation of a parameter, theta, and a random vector u. I'll point at that, it's highlighting instead. A random vector u that's drawn from some tractable distribution phi. So if we can phrase the simulator like that, and this is going to work better for some than others, but if we can do that, then it helps us a bit, because we can replace the integrand in the ABC likelihood that we had previously, which was this thing here, with this thing here, which is where we've replaced the x here with this deterministic function of theta and u, and all the randomness now is in this tractable distribution phi here. So we've still got an ABC style likelihood. We've still got this pi epsilon here, but the intractable f bit has gone, and that means that we can do things like exploring the joint space of theta and u with other algorithms. So essentially, we've just got more parameters to look at now. U. So this isn't always going to help us, because in some cases, U might be something that varies in dimension for different simulations, this kind of thing. So it's not going to, and sampling on those kind of spaces is difficult. So it's not just going to magically solve all our ABC problems, but it is it does come up often enough, and is a useful thing to do. So so our intuition here is that, just to think of this another way maybe, is that in the standard ABC algorithm, for every theta that you simulate, you're simulating the x's from the model independently every time. And you're not using any information about the fact that some x's are going to be less useful for different thetas. Okay. But in standard ABC, you're forced to generate it from f, and you don't really have a choice in this. Here we could maybe tailor the u variables so that they're going to give us things that are closer to the real data. That's the advantage of exploring that space. So if we can do that, then we can set up an algorithm that is essentially particle MCMC for ABC. So rather than using an importance sampling estimator of the likelihood, we can use a sequential Monte Carlo instead, and that's going to help us because we can, in some cases, the cost of that to stabilize the variance can be quadratic in D rather than exponential. So this can help us. So this is what was investigated in this previous paper. Again, I can't point to this line here, Prangal et al. 2018. Where we used SMC to estimate the ABC likelihood when we use this this construction with the deterministic transformation. So for every theta, we're going to run an SMC algorithm to estimate the likelihood. That is so that worked pretty well. I've got some results on the next slide, or a couple of slides time, in fact. Just a point at this stage, that is not ABC-SMC. ABC-SMC is something different. ABC-SMC is really kind of intuitively the idea of using SMC to explore the theta space, whereas here what we're doing is exploring the space of the u variables conditional on theta. So we've got an MCMC algorithm for exploring theta space, and then for each time we have the likelihood, we have an SMC. Okay. So so here's what the algorithm looks like. So it has a sequence of distributions that looks like this. So this is for a fixed theta, okay? And the reason it's called a rare event algorithm is because we're looking at the, I should have included the equation on this slide. We're trying to look at the, use these simulations from the model that we're doing, or U when we can do that, to look at the probability essentially of falling in this small region that's close to the data. So you can think of it like this. You've got some, this is the complete space that you can simulate from, and you're simulating these points, and you've got to fall, these points have got to fall inside some region here that's close to the data. So this is like a rare event problem where you take the probability of some extreme region or something. And there's this algorithm that uses a standard SMC sampler that estimates the size of those regions. Okay, so essentially in ABC we've got the same kind of problem. We want to estimate the probability of this thing under F. which this is the pi epsilon under F. And so what we do following that paper is we set up a sequence of targets like this. So this is the final target. This has the epsilon that we're aiming for. So in ABC-SMC, you set an epsilon to start with, and you're going to try and run with that. So your first target is going to look like this, where epsilon is very big. So if epsilon is infinity, then the pi epsilon has no effect. So we just have this thing here. And then we're going to reduce epsilon throughout this algorithm. So this is, again, for fixed theta, remember. We're going to reduce this epsilon, and we're going to shrink the size of this this ball, essentially, that we have to look at. So you can think of like the pi epsilon, sorry, the phi here being the drawing from this square. And you can think of the pi epsilon here is giving you balls of decreasing size. So this might be the first one, then we have this one, then we have this one. And we're looking at estimating we're looking at estimating the integral of this distribution defined by the ball here with respect to the wider distribution. So the probability of falling in that region, essentially. Okay, so that's the sequence of distributions we use in that SMC. Cancel, move like that. There we go. So we're going to stick to the uniform kernel here just to make things simple. But of course, this can be generalized. So the rare event algorithm looks like this. These are the steps. This is the SMC algorithm for a fixed theta. You draw a bunch of points from the proposal. That's the things in the square that I drew on the last slide. And then we're going to reweight each of these points where we're going to get a weight of 0 if we fall outside the ball. So this is the ball defined by this distance being less than epsilon. And we're going to give them weight 1 if they fall inside. I mean, that obviously isn't giving us a distribution, but we can easily find the normalizing constant of that if we wanted to. But that's giving us our weights. For the SMC, it's not going to matter because we're going to normalize these weights anyway. So it doesn't actually matter unless we're doing things to do with marginal likelihoods, which we're not going to discuss here. So, sorry, distraction. So we generate all these things from the big box, and then we weight them where they get a weight 1 if they fall inside the ball, and a weight 0 if they don't. And then we resample. So we're only going to keep alive the ones that fall inside the ball. And then we're going to do an MCMC move that moves them around within the ball. Okay, we've got this part here as part of our target, so they'll get 0 weight if they go outside the ball. And we run that again and again where we decrease epsilon until we get to the epsilon we want. In order for this to work well, we need the MCMC to mix, and we chose a slice sampler to do that in this previous paper. I guess you could do some kind of adaptive MCMC as well, where you adapt as the ball shrinks. And then the estimated ABC likelihood is the product overall of these SMC iterations of the average of the weights of each step. So what does that look like? It looks like this. So this is a nicer version of my the box I drew. So we simulate a bunch of U variables from the box, and then at step 2 we have this. Here it's an oval, not a circle. These are the things that are close to the data here, and then all the black ones get 0 weight, all the red ones get some weight, and then we do a resample and a move, which gives us the blue particles. And then we do it all over again. So we're going to shrink epsilon, and then some more will fall inside the ball, etc., etc., etc. So what we get from this is that if you started out with these U variables and you went straight to this one here, then you haven't got a very good Monte Carlo estimator, because not many of these, it may be the case that many of these U variables don't fall inside the ball, and so we get a poor estimator of the probability. Okay. Please ask questions if anything I'm saying doesn't make sense, by the way. Okay, so that's how the rare event thing works. And then we looked at it on an example. So I haven't written down what the example is. I'm just going to explain it because it's relatively simple. So we've got the model is a Gaussian distribution. We've got the parameter we want is the standard deviation, and we've just got some uniform prior on the standard deviation. And we want to estimate the posterior distribution of the standard deviation from 25 draws from the normal. So in ABC, this is the kind of dimension that would start to give us problems. So what would we do in ABC? We'd pick a standard deviation, we'd sample from the normal distribution, which would give us something, 25 points from the normal distribution. And then we compare kind of point-wise each of these 25 points with the 25 points that are in the real data. So we're comparing two data sets that aren't quite high dimensional, but we're getting towards where the important sampling estimate is going to fail. And so what we see here is, on the left here, we've got the root mean square error of the different algorithms. And on the right here, we've got the efficiency in time for ESS, time for the effective sample size. And what's going on in both these pictures is that as we go this way along the graph, the threshold, the epsilon, the bandwidth is getting smaller. This is the regime where it's going to get harder to estimate the likelihood. And the lines that are distinct from the others here are ones that are using the rare event algorithms. These are the ones that, in fact, go further down here as opposed to these ones. And what we see is that as the threshold gets smaller, the rare event algorithm can carry on squeezing the epsilon smaller and still be able to estimate the likelihood. Essentially what happens in standard ABC is as you squeeze the threshold too small, you don't get any simulations that are within the right region. And you can, if you've seen properties of high dimensional spaces, it's not going to take too much in imagination to realize that we're not going to get close to where we want to get close to if we're just simulating, if we want a small region and we're just simulating from the model. So what we see here is that as the epsilon gets smaller, these other algorithms blow up and the rare event algorithms don't as much. And we can get further down in terms of root mean square error on the rare event algorithm. Okay, so I think that's not too bad for time. So what we see is that the rare event ABC beats the standard ABC as the dimension of the data grows. So that I haven't shown that there. I've just shown as epsilon shrinks, but we have a similar effect there, right? The variance of the likelihood estimator is getting bigger. And we don't suffer as much when we use sequential Monte Carlo for estimating the likelihood compared to importance sampling. So for those who know about particle filters and things, that's probably not very surprising. In fact, I guess for most people, it's not very surprising. It's the same reason that particle MCMC can beat just doing an importance sampler to estimate the likelihood. So that algorithm is very useful if you can use this decomposition of the simulator. But something that is kind of standard in ABC is to choose epsilon here so that it gives us a nice algorithm. Okay, so being very vague there. So if you run ABC-MCMC, you choose a fixed value for epsilon to start with, and then you run the algorithm typically. Whereas in ABC, what people usually do is, it comes from the ABC rejection, I guess, is do a bunch of simulations and then choose epsilon to be small enough that you can, the smallest value you can get away with, okay? Which means that if you just naively simulate from the prior and then the model, sorry, then it would mean that, say, I get 100 or 1,000 things within the region with close to the data. You pick the best 100 or the best 1,000. Whereas you can't do that with ABC-MCMC. It's, it works sequentially, and you have to pick an epsilon first, and then you run the algorithm. So the way that lots of people get around this is by using ABC-SMC, which uses MCMC moves usually within the algorithm. And what happens there is that's an SMC algorithm on theta space. Okay, so you start out with the prior, and then you're going to make the epsilon smaller and smaller and smaller to get you to the posterior. And the algorithm, I meant to write this on the slide, but forgot to add it in. We'll go like reweight and then resample and then move in theta space. So you have an ABC MCMC move for moving in theta space. So you shrink your epsilon, and some things will die off, some things will be kept because the things with 0 weight will disappear, and you resample, which has keeps the ones that you are good. And then you do an ABC MCMC move on every particle, and then you go around again. And you do keep on reducing epsilon. And in fact, the nice thing about this algorithm is that you can reduce epsilon adaptively by looking at the effective sample size as you're going down. Essentially, the number you pick the sequence of epsilon such that the sampler never dies off in some ways, or such that the number of points that fall in the region never goes to 0. Okay, and eventually what will happen is you run this algorithm, and eventually you'll get to a point where you can't reduce epsilon anymore because you're not getting any simulations in the right region, and that's usually when you stop. Or maybe you stop when your ABC MCMC stops mixing, because that's another effect. When you reduce epsilon, the variance gets bigger, and so you get a worse mixing MCMC, and so you have to stop running the algorithm. So that's what most people do. But in the previous work, we've got an ABC MCMC where we can't do that. So the obvious thing to do is to try and combine them. To try and do an SMC algorithm on theta space that uses this SMC for estimating the likelihood each time. So this is why it's an SMC squared algorithm. What we're going to have is we're going to have an SMC algorithm on theta space, and then for for each theta, we're going to run an SMC algorithm on the X space or U space as it is now that we've moved to. Okay, so that's the plan. So I'm not going to give the full algorithm here for writing it out in maths, because I think it looks complicated in the talk, and I'm not sure how well it would come across. So I'm going to do it with pictures instead, but just something to fix beforehand. In ABC-SMC, what you would really like it to do is to use the exact ABC likelihood at every step. So that would be doing the, in the weight update, you end up having the, if the prior is staying the same, you end up with the likelihood ratio for the different target distributions ends up being your weight update. And that's this thing here. So ideally, we'd like to use this, which is the true ABC likelihood in the numerator and the denominator. But of course, what you really do in ABC-SMC is you estimate this this ABC likelihood with the thing that we talked about at the start. It's the simulate from the X space or U space as it now is, and then average how many times we fall in the in the ball, essentially. So this is the standard ABC-SMC algorithm, and so it uses an SMC on the theta space and the importance sampler here for estimating the likelihood, which includes the weight update and in fact in the MCMC. So what we're going to end up with in the ABC-SMC squared is we're instead going to be using the internal SMC to estimate this ratio. Okay, so that's the thing to bear in mind. We're going to be looking at estimates of the ratio of the probabilities of these regions under phi. These regions being this region here and this region here, defined by these ABC terms. I hope some of you are still with me. Okay, so here is a pictorial representation of ABC-SMC. Hopefully that's the lines are all thick enough for everyone to see here. I'm going to run, in inverted commas here, an ABC-SMC with 2 theta particles. So these big boxes here are the theta particles, and this is time 1. So time's going to increase as we go down the slides here. Okay, and I've got 2 theta particles here, and you'll see why they're big boxes in a second. Here we go. So for each theta, I've sampled some u variables, which are the little black points here that maybe you can't see. Can I zoom in? Yeah, there we go. There we go. Maybe that's a bit better. The little black points here are the u variables, and in the weight update, we're going to estimate the probability of the circle region under the points distributed from the square, and so we're going to look at the sort of the number of these that fell inside the red circle here, and that's going to give a weight update, our likelihood estimate at the first iteration, and then we do the same for the second particle, which of course has its own set of u variables or x variables if we're using the standard setup. So that is standard ABC-SMC first iteration weight update. So that's what the key is saying here, that we're doing the weight update there. Okay, and then at the next iteration, we have a there's a resampling step that happens between here, but we've kept these 2, theta 1 and theta 2. So these ones didn't die. These things here, these particles didn't die when we resampled. And we didn't do an MCMC move at that step, or maybe those things there, yeah, I haven't shown it basically. So those things there remain in the population, because remember our steps are in the external algorithm: reweight, resample, and then move. So I haven't shown the resample and move steps here. Let's just assume they made it through to the next step and the MCMC was rejected. So they are as they were. They're the same theta values. And if you look closely, hopefully you can see that the little black points are the same between them. So we're using the same set of u variables that we had from the previous iteration. So then what happens is you do a weight update. That circle really isn't very visible, is it? Sorry. We do a weight update, and we use these black points here to estimate the probability of this region again, and that's our weight update. And it's also what we're going to use in the MCMC if we were to do a move. And we do the same for the other particle, and then we resample, and then we move. So in this case, I am going to do a move. I'm going to say that theta 1 here we're going to have a proposed value of theta that is a candidate to replace the current value of theta 1. That's this thing over here. It has its own u variables, and its likelihood is estimated by looking at the how big that circle is, essentially estimated by the black points. And if that likelihood is estimated to be bigger than the current one, this one here, then we'll accept. And I have tried to represent that using this. So particle 1 has been replaced by the theta star. Okay, so in our new generation, we have this new value, and just the key thing here is to know what's going on with the black points. So hopefully you can see from that thing that zoomed in that for theta 2 here, the black points, can I draw? Yes, I can draw. The black points are the same between here and here, but here when I've accepted, no, I'll do that. There we go. Now I've accepted this move here. These black points here are the same as these black points here. Okay, so that's the theta, and the u has been carried over and has replaced the theta 1 particle. So that's standard ABC-SMC. And then in the next step, we will try and estimate the the probability of falling in this circle, and that is getting harder with this set of black points drawn from the box. So this is where ABC-SMC is going to fail. We get to the point where the circle gets too small for us to be able to estimate reliably its probability. Okay, so and remember, our only mechanism for updating u or x is is by drawing them from F, which is what we've done here. We've drawn the theta, then we've drawn these black points from F, which is the big black box. or phi if we're looking at the U construction. So this is the difference between this algorithm and the rare event algorithm. So this should show you the why this algorithm is going to be more effective, just intuitively. So we start out with the same setup. We've got parameters in theta space. We've got two of them. We've got two particles at time 1. And then the first step is the same. We simulate for those things. We simulate from phi. So this is the internal bit now. So inside these boxes. And these things here look very like what we had on the previous slide. In fact, I think they're probably the same they were on the previous slide. We've simulated from phi. That gives us these black points. We've got these things to help us estimate the weight update, and everything's the same. But the next step is different because we're going to do SMC moves within each particle. So each of these U things now isn't just an importance point, it's an SMC particle. And the first thing we're going to do is we're going to resample them and we're going to move. So the ones that are inside the circle are going to live and then move, do an MCMC move. Some of them are going to change position. And the ones that are outside here are going to die. Okay, so we resample. We've got the same number of particles as we had previously, but now they're all inside the circle, and then we move them. And I think here all of them are moved, which isn't very realistic. This isn't going to happen really, but this is just an illustration. This is what happens if we ran our MCMC for long enough that they all moved. Okay, so we've got a different set of black points now, and the same happens for the other particle. And then we move to the next step. So this is the next step of the external SMC. We carry forward here for particle 1. Let's concentrate on that one. We carry forward all the particles, all the internal particles to here. So you can, I'll draw circles around the ones that are the same, like spotting constellations or something. We've got these things here are the same as we go forwards, and here we see the advantage. So now we have to estimate at each step the weight update is the relative probability of being in the internal ball compared to the outside one. Okay, so that's the probability. That's the weight update that we're using, and we can now estimate that using points drawn essentially from the red circle, which is now turned into the black circle on this here. So that's going to, because we haven't got all these points in the corners, that's going to give us on average a better estimate than if we're drawn from phi. And then we do the same over here. We have the same thing that happens for the other particle. And then we do the same thing again internally. We do a resample of these U points and we do a move. So that gives us a set of points that are in this red circle. And that's going to set us up better for the next step. So the next step looks like, what have I done there? It looks like I've changed. I don't know whether I've changed anything there. Let's just skip forwards. Oh no, there we go. Sorry, right. It's this thing here that's changed. Okay, so we're going to now propose a new theta. So we're going to do an MCMC move before we get to the next iteration. Okay, that's on theta space. Now, how do we do that? Well, we propose a new theta, and then we propose lots of new U variables from phi. But then to make sure that this is all in the same space as these things here, we have to follow through. The proposal has to do the internal SMC all the way up to the current iteration. So that's what's changed between this and the next slide, because we've done for this new theta, we've proposed a new, we've had to follow, this is where it gets a bit more expensive, we've had to follow the entire internal SMC process to get us to here. But then after doing that, that gives us a likelihood estimate, and we can then compare that with the likelihood estimate we've got from here, and that was our, and then we decide we have an accept reject step in our actually what's going on is it's a whole rare event MCMC move, just like the ones I presented in the first half of the talk. And in this example here, I've accepted it. And you can see that the black points here are here. So it carries over its particles with it, its internal particles. And then obviously these points here are going to be better at estimating this ratio of the areas here, or estimating the likelihood that they're going to give us a lower variance estimate. So we've got particles here in the internal space that are going to help us estimate the likelihood a lot better. Okay, so that's the difference between standard ABC-SMC and the new algorithm that we're proposing. So the proof that this works is essentially the same as the one in the original SMC squared paper for state space models. I'm not going to show any of that here. I'm just going to show you a result. I'm nearly out of time, I think. So we haven't got lots of results for this yet, but we have got some. Here is an example of in the Gaussian example again. So so what am I doing here? So we're looking at the 25-dimensional Gaussian again. We are looking at comparing ABC-SMC with the rare event algorithm. There was a question a bit before the talk as to how you compare SMC algorithms. A way that we can do in this case is to look at the here we're adaptively tuning the sequence of epsilons, and where we have a higher effective sample size from our particles, it will allow us to decrease the tolerance more quickly. And that's what we see when we compare these two SMC algorithms. We compare the original ABC-SMC with adaptive tuning of the tolerance, and we get the top line here. And if we compare that with the new algorithm, this is only per SMC iteration. So this is, well, let's just say this first. We reduce to a smaller epsilon quicker. And in fact, probably this thing here will stop being able to decrease well, not in the not too distant future, just because we won't be able to get points that are likely by simulating from the Gaussian itself. But where we have this process that I've just shown you, adapting the black points to be in the right place, then we can squeeze things to be a lot smaller. This isn't taking into account computational effort. So the computational effort is a bit bigger for the rare event algorithm. It's actually going to be most where we propose a new theta, because then we have to do the whole process again in terms of refining these black points. But even taking into account computational costs, we know theoretically this should work better, and that's what we've seen in practice as well, that we can look at higher dimensional things with smaller epsilon because we are using an SMC rather than an importance sampler for estimating the likelihood. Okay, so that's where we are. So let's conclude. So we've combined the nice properties of using the sort of particle MCMC style approach to ABC, and we've combined that with the ABC-SMC style algorithm that's favored by the ABC community. So compared to ABC-SMC, we should be able to look at higher dimensional data and hence higher dimensional models. We are limited to cases where we have this construction for the likelihood for the simulator, sorry, and we can usually write things in this way, but the problem we'll end up with is it will be very difficult to explore the space of view for some models. And then, yes, so compared to the previous work on the rare event ABC-SMC, we have the SMC exploring the theta space, which is more appealing in lots of respects in ABC. Okay, so that's that.